Hi there. In this video, I'll be detailing the construction of a fifth axis from my small CNC milling machine in my home workshop. The first part of this video details the 3D design of the unit. I then go on to the machining and assembly of the components. I then talk about the Linux CNC configuration and post-processing elements of the project. And finally, a first test piece is manufactured to assess the performance of the unit. The design has been uploaded to GrabCAD. The link is in the description below. In this design, there are only 5 components to be manufactured. The steel plates used are between 10 and 16 mm thick. The components are held together with M6 Allen cap bolts. The fifth axis configuration here is an AC configuration. That is, the fourth and fifth axes run parallel with the X and Z axis respectively. The unit is very rigid and should be more than adequate for use on my small milling machine. The servo motors used are harmonic-drive based with cross-roller bearing outputs. This ensures near zero backlash and high axial and radial rigidity of the output horn. So on to the manufacturing of the fifth axis. XC48 carbon steel is used for all of the plates. For the A-axis base plate, I started by cutting some 15 mm plate to size. The plate was then mounted in a 4-jaw chuck on the lathe and faced on both sides. The plate was then mounted on the milling machine using strap clamps. The sides were milled to square up the plate. The under and front sides of the plate were then hand scraped to ensure flatness and perpendicularity. Hand scraping carbon steel takes a bit of effort. I used the scraping blade profile published by an Austrian engineer on YouTube called An Engineer's Findings. This worked very well. A link to his video detailing the profile angles is in the comments below. The 10 mm mounting holes were then spotted and drilled. The holes used to attach the A-axis servo plate were then spotted and drilled before being tapped to M6. We now move on to the A-axis servo plate. This component was fabricated from 12 mm plate. After the sides were faced in the 4-jaw chuck on the lathe, the hole patterns were spotted and drilled on the milling machine. The holes were then countersunk with a 10 mm flat end mill. The plate was once again mounted on the lathe, and the holes that locate the servo motor was brought to size. Back on the milling machine, the sides were milled to the profile. During the curve milling, the Y-axis stepper driver raised an alarm. This caused the Y-axis to stop while the X and Z axes continued normally. This resulted in a gouge being taken out of the curve. The same problem happened again later while machining the C-axis servo plate. I'll discuss later in the video the solution I came up with in order to prevent this happening in future. With the machining complete, the plate was attached to the A-axis base plate. A quick rigidity test was then performed. With a good deal of force applied, there was not much more than 20 microns of movement. With the A-axis servo mounted, a check was made on the granite plate to check the perpendicularity of the horn's outer surface. Using a precision square, no light was visible in the gap, and a 40 micron feeler gauge would not fit. The next component was the A-axis horn connector. This was machined from a 20 mm piece of 70 mm OD bar stock. An important dimension here is the 14 mm backside tenon. This feature is used to locate the component on the servo's horn and was turned to a snug fit. Back on the mill, the hole pattern was spotted. The holes were then drilled. The servo mounting holes were then countersunk using a 10 mm end mill. A slot which locates the C-axis servo plate was then milled. The OD was then turned on the lathe to final dimensions. We now move on to the C-axis servo plate. This component was fabricated from 10 mm plate. After the sides were faced in the 4-jaw chuck on the lathe, the hole patterns were spotted and drilled on the milling machine. The holes were then countersunk with a 10 mm flat end mill. The sides were then milled to the profile. The plate was then mounted in the vise on the mill and the side holes drilled. After the hole that locates the servo motor was brought to size on the lathe, the side holes were tapped. So here's the A-axis servo horn connector connected to the C-axis servo plate. The slot is a very snug fit. 5 M6 Allen cap bolts further secures the two components. The final component to manufacture was the rotary table which mounts onto the C-axis servo horn. This component was machined from a 20mm piece of 100mm OD bar stock. The top surface was faced on the lathe. After spotting, a pilot hole was drilled before drilling a 10mm hole. On the back side, a 14mm tenon was machined to locate the component on the C-axis servo horn. Back on the milling machine, the 4 M6 mounting holes were drilled and countersunk. Next up was the milling of the slots. A T-slot cutter was then used to mill the T-slots. Back on the lathe, the OD was turned and chamfered. With all of the machining complete, the fifth axis was assembled. I haven't weighed it, but it is heavy and very solid indeed. There's no detectable backlash or radial or axial play in either of the joints. The configuration of Linux CNC for 5 axes was quite straightforward. I started with the existing XYZAC TRT configuration. The StepConf wizard can't handle 5 axes, so I added the A and C configurations manually. As these are rotating axes, joint limits, steps per degree, max angular velocities and max angular accelerations were specified in the .ini file. The servos are running in stepper control mode and are connected directly to the parallel port. No additional drivers are required for them, so step and direction pins on the parallel port were allocated for each servo in the .hal file. With this fifth axis design, the line of rotation of the C-axis is perpendicular and intersects the line of rotation of the A-axis. Axis offsets can however be specified in Linux CNC. This should allow us to compensate for inaccuracies in the alignment of the axes. The configuration also allows us to deal with the situation where the top of the rotary table is not in line with the A-axis, as is the case here. I'll talk more on this later in this video when configuring the test piece. As mentioned earlier in this video, an intermittent alarm was being triggered by the Y-axis stepper driver. This resulted in some minor gouges but could have been much more serious. After viewing the TB6600 stepper driver's circuit diagram, I made a minor change to the PCB and extended the alarm signal from each of the 3 stepper drivers to the parallel port. The alarm signal is active low, so I created a 3-input AND gate in the Linux CNC configuration and routed the output to the emergency stop signal. I also added alarm LEDs to the PY VCP panel to indicate the status of the alarm outputs. For Fusion 360 post-processing, I used the Linux CNC 5-axis post-processor. Only minor configuration changes were required. These changes involved specifying the axis type and rotation limits and directions. With the construction of the 5th axis complete, it was time to test it. After some head scratching, I decided to machine an ashtray for a friend. The design of the ashtray was quite simple, with only 5 operations. From the perspective of Linux CNC, the WCS origin of the 5th axis is at the point of intersection of the A and C axes. This means that the WCS of the 3D model must be set to the same point in 3D space. To simplify this, the rotary table was modeled. Additionally, a spacer representing the gap between the underside of the rotary table and the A-axis center of rotation was added. A blank was then prepared for the ashtray. A piece of 70mm OD aluminium bath stock was prepared on the lathe. One side was faced, then a small groove was turned. The other side was faced to length and turned to the required OD. A shallow 10mm locating hole was then drilled. The fifth axis was bolted to the milling machine table, then dialed in along the X-axis using the side of the base plate. The A-axis was jogged horizontally using the surface of the rotary table to dial it in. The A-axis was then touched off to G54-0. The 10mm hole at the center of the rotary table was used to dial in the G54 X and Y 0 points. The stock was then placed on the rotary table and located using its 10mm hole. It was then clamped to the rotary table using the strap clamps. The stock top height above the A-axis center of rotation was then calculated. The G54 Z point was touched off to this figure. The first operation was a multi-axis swarf operation. This is a true 5-axis operation as all of the axes move throughout the operation. The continual movement of the Y-axis stepper can be seen from the footage. The surface finish was surprisingly good. I expected to see undulations on the surface with the constant in and out movement of the X and Y axes. The next operation was a simple 2D pocket. The next operation is a multi-axis swarf operation that will clean up the 2D pocket. From the footage, we can see some machining marks from the 2D pocket were not cleaned up. This is likely due to a small misalignment of the A and C axes. I will need to investigate this. Next up are a series of 2D circular operations. These are 3+2 operations and take advantage of Fusion 360's tool orientation feature in order to move the A axis to 90 degrees. Next up are a series of 3D project operations. Once again, these are 3+2 operations that take advantage of the tool orientation feature. A 1.25mm radius ball end mill was used for this series of operations. With all of the operations complete, the underside of the ashtray was parted off on the lathe. The marks left behind from operation 3 were also cleaned up. Finally, some Scotch-Brite was used to tidy up the engraving. To conclude, here are some observations. I'm very pleased about how this project went. The accuracy of the test piece was acceptable and the surface finishes were surprisingly good. A future conversion to a BC configuration may be useful as the AC configuration is somewhat restricted by the limited Y-axis travel of these small milling machines. A further observation is that multi-axis operations are quite limited in Fusion 360 manufacturing. Unfortunately, the manufacturing extensions module is rather expensive and probably out of reach for most people. So thank you very much for watching. If you enjoyed this video, please like and subscribe.